This video is to talk to you about wave motion and compare that to what we already know about simple harmonic motion. We have previously seen that any mass spring system or any pendulum experiences simple harmonic motion. What that means in terms of a displacement versus time, velocity versus time, or acceleration versus time graph is that it's going to follow the path of a sine or cosine wave. What we mean by that is depicted in the following simulation. I have a mass spring system. I have decreased the frequency to minimum in order for you to see what's going on. And watch when I hit play. Through equilibrium, up to its highest point, maximum point, back through equilibrium, minimum. Equilibrium maximum, equilibrium minimum. 2 complete cycles here. And you'll see that 2 complete cycles also happen with the velocity time graph, because you have 1 up, 1 back to equilibrium, 1 down, 1 back out, 1 back to equilibrium, which is consistent to 1 wavelength, which is going to be the same wavelength as what you see in the displacement versus time graph. Also, you've got an acceleration versus time graph, where you look like you have a cosine wave, where it goes to equilibrium, down, back up to equilibrium, back up to its maximum position. And of course, the acceleration is low because I have the frequency at a minimum. So this is what I mean when a sine or cosine wave is created whenever you've got simple harmonic motion, or at least the pattern can be graphed with a sine or cosine wave. Here is the anatomy of any sine or cosine wave. You might have seen this before in pre-calc or algebra 2. So there's 2 ways to define wavelength. If you start from the equilibrium point, you go up to the maximum position, back through equilibrium, down to the minimum position, back to equilibrium. That's considered a wavelength. Also, if I go crest of one wave to the crest of another wave, that's going to be the same distance. That's also considered a wavelength. So as I've already implied, the maximum positions away from equilibrium are considered the crests, and the minimum positions away from equilibrium are considered the troughs, equal and opposite of the crests. We also call these crests and troughs the amplitude of the sine and cosine wave, which would be in math class the coefficient in front of sine or cosine to say how tall your waves are actually going to be. And again, here's 1 complete cycle, which is the same distance as a wavelength from here to here. And you'll see equilibrium, top of 1 crest, equilibrium, bottom of the second trough, back to equilibrium. 1 complete cycle, 1 complete wavelength. This down here is saying this wave is moving in this direction. This is a typo, so I thought I'd add a cow graphic here. Imagine that when you create a disturbance in a medium, that this wave is actually moving this distance. And that's what's going to lead us to talk about wave motion. So wave motion, a disturbance that causes a wave in a medium, is considered wave motion. And so here is a system that wave motion has appeared. Get a drop of water hitting another lake full of water, and that has created a disturbance, and that disturbance has created waves. Wave motion occurs when a disturbance travels through a medium. The medium in this particular point is going to be the water. The medium can also be air. It can also be an object. So this is the difference between simple harmonic motion and wave motion, is that wave motion transfers energy, whereas simple harmonic motion will actually just transfer a particle back and forth and back and forth. So remember that I mentioned that waves transfer energy and not particles. So my disturbance is going to be this wrench. The medium is going to be the string of beads. Now watch what happens when I create one disturbance on the string. The energy travels down the length of the string of beads. However, the beads themselves remain in the same horizontal position and do not travel down the length of the string. The beads do move vertically, but they do not move horizontally. This is why this is a great representation of wave energy. Now, if I was to restart this, and instead of doing one simple pulse, I will oscillate. Notice there's the sine and cosine wave again. But this is created because the disturbance is moving down the length of the string and then bouncing back again. And because of that, it's the appearance of a sine or a cosine wave. Whereas a pendulum or spring will make this appearance of this wave itself because of its constant back and forth motion. This simulation is going to be attached to the Schoology page so you can play with it. Big takeaway here, waves transfer energy, not particles. Those particles are not moving down the length of the string. Those particles are moving vertically to the string. The wave is transferring energy. There are two types of waves, mechanical waves and non-mechanical waves. Mechanical waves require a medium in which to travel, air, an object, water. There is only one type of non-mechanical wave. We've talked about it before in a previous unit, and think about that and you can guess again what that is by the end of this video. There's also two types of waves, transverse waves and longitudinal waves. Transverse wave will create a disturbance that is perpendicular to the medium. A longitudinal wave will create a disturbance that's parallel to the direction the wave will be traveling. And let's see what that looks like. So here's a longitudinal wave. Notice that the disturbance is going parallel to the direction the energy is going in the slinky. Whereas a transverse wave, the disturbance happened perpendicular to the direction the energy is moving. That's the difference between a transverse wave. How can we calculate the speed of a wave? Really important to know, waves do not accelerate their velocity. That means that when a disturbance travels in a medium, that disturbance will travel at a constant velocity. And constant velocity, first uniform equation of motion, is distance divided by time. Well, we consider the distance a wave travels as a wavelength. So a wavelength is depicted with this symbol lambda. And again, it's a measurement of the crest of one wave to the crest of another wave, or from equilibrium to maximum, back to equilibrium to a minimum, and then back again. That's a wavelength. Capital T is time period, how long it takes for the wave to travel a wavelength. Divide those two terms, you get the velocity. We also know from the previous video that time period is 1 over the frequency. Therefore, if I smash these two equations together, I'll have velocity equals lambda divided by 1 divided by frequency, which means that the velocity of a wave can be found by multiplying the wavelength times the frequency. And so I have put this in the little box here. Velocity equals frequency times the wavelength. We measure wavelength in meters, frequency in hertz, 1 over seconds, and velocity in meters per second. Now back to that non-mechanical type of wave. Electromagnetic radiation is made from photons, which is neither mass nor energy, and they travel through the air with little tiny, and not even air, in space as well, with little tiny waves. Since electromagnetic waves do not travel through a medium, don't need to travel through a medium, they all travel at the speed of light. So whenever we've got light from the sun that's traveling to our Earth, all of those photons are traveling at 2.9989 times 10 to the 8th meters per second. We round that up to 3 meters per second. Absolutely fine to do. Most scientists do. And the speed of light is denoted with lowercase c for the variable for the speed of light. So in order to find either the wavelength of any type of electromagnetic radiation, the frequency of any type of electromagnetic radiation, you can use the speed of light as the constant. So this equation right here, speed of light equals lambda times frequency, will allow you to either find wavelength of EMR or frequency of a different type of electromagnetic radiation. You are now ready to do the following problems. Page 387, 1 through 4, page 388, 1 through 5. Use those equations. There are some thinking questions in there. And when those thinking questions and conceptual questions come about on page 388, go back and reference that simulation that I've also attached to your Schoology page. Almost under 10 minutes long. Hope you have a good night.